So today I'm going to talk about some critical data analytic issues in smart city ITS data evaluation. But these fundamental issues that I'm going to talk about today also apply to all transportation data analysis and in many respects, to data analytics beyond the transportation field, because there are going to be fundamental elements relating to unobserved factors, human behavior, and so on. So I'm going to get into that in a few seconds. But first, let me look at the need for data analytics in terms of smart city ITS projects. We can think of it, there's at least two important elements. One is that you want to evaluate the effectiveness of an implemented smart city ITS project. So you've done something, it's implemented, you want to know how effective it is. The second one is you can use data analytics potentially to determine the most appropriate and effective smart city ITS project, the one that you should implement. Now, some of the elements that I'm going to talk about in a few minutes are going to expose some of the difficulties in doing both of these tasks, okay? So let me look at the four key issues that I'm going to address in this talk. The first one is unobserved heterogeneity. And I should mention that all four of these issues, I've recently wrote papers on all four of these things. And at the end of today's talk, I'll give you the references so you can explore each of these individually in more depth if you have time. So the first one is unobserved heterogeneity. And unobserved heterogeneity basically arises from the fact that when we collect data, there's always something that we cannot collect, very complex behavioral process or something that we do not collect. So there's observed heterogeneity, which we can look at the data that we do collect and we observe the heterogeneity in the data. But then there's the unobserved aspect of it, the data that we do not directly observe. So I'm going to talk about statistical and econometric techniques that have been developed in the last decade or two that address this issue of unobserved heterogeneity. The next one is going to be data size and the prediction causality trade-off. So in years past, you have a couple thousand observations. That's about the maximum data size that you would get. But in today's environment, you can have hundreds of thousands, millions of observations. So data size is going to limit what analytic approach you use. But there's also the analytic approaches that tend to be very good for large data are not very good at uncovering causality. So they're good for large data, they're great for prediction, but they don't uncover the causal effects. So I'm going to talk about some of the trade-offs involved there. The third point is what I'm going to call temporally shifting model parameters. And really what's happening here is human behavior is changing in fundamental ways over time. So there's sort of a long-term trend in changes in human behavior. And then there's human behavior that would change in response to a project that you built, sort of a localized, immediate change in human behavior. So I'm going to talk about how you might deal with these changing behaviors. And the fourth point that I'm going to talk about today relates to the compensating behavior of users. So what this refers to is sometimes you may implement an ITS strategy to improve safety. And what you find out is that safety doesn't improve at all, or it improves much less than you thought. But the reason for that is that people have compensated their behavior, right? They found that the facility is safer, so they might decide, well, it's safer now, I might drive faster. And so the benefit is not extracted necessarily in safety, but could be extracted with greater mobility. And again, I'll talk about this, give it an example as we move into each one of these topics individually. So the first topic that I'm going to deal with is unobserved heterogeneity. So data collected for the analysis, no matter what analysis you're doing, can never be complete. So there are statistical methods that have been developed to account for the fact that you do not have complete data. An example would be that you observe a vehicle in a crash. You may have information on the driver characteristics, but you don't have the detailed information on where the impact was on the vehicle, how the energy dissipation happened throughout the vehicle. So there's going to be a lot of things that we're not going to be entirely able. Even if you have a fully instrumented vehicle, there's still going to be things that you're not going to be able to entirely capture. So the way that this has been dealt with in statistic and econometric fields has been to use mixing distributions that assume that the heterogeneity that occurs throughout the population can be represented by some parametric distribution. So when we think of the use of mixing distributions, the most obvious one that comes to mind would be what we call random parameters models. So what these models do, instead of estimating a single parameter for the entire population, is they allow the parameter effect of the explanatory variable, the effect of the explanatory variable, to vary across individual observations. So if you go through the transportation data analytic literature, you will see the application of random parameter models in the last 2 decades have become quite extensive. Similar to random parameter models, we have latent class models. So the idea is that unobserved heterogeneity does not necessarily vary from one observation to the next, but there are groups of observations or latent classes that share the same marginal effect or the same parameter values. So instead of having individual parameters per observations, you have groups of people, classes, groups of observations that have the same parameter. The third approach is what I call the Markov switching models. And I've done a couple research papers on Markov switching models. So the idea of Markov switching models is that the parameters that you estimate may vary over time between 2 or more states. Now, conceptually, this is a really interesting idea, but it's very difficult to estimate these models. I have one research project where we use supercomputers to estimate estimating. It's a very difficult estimation procedure, but it's a good conceptual theory, is that you can view observations as switching between multiple states. So all of these models, random parameter models, latent class models, I'm going to refer to these as heterogeneity models. And we're going to come back and talk about these in a few seconds in a little more detail. So what happens if you ignore this unobserved heterogeneity? Well, you can show mathematically that you'll get biased model estimates. You can get erroneous inferences and conclusions. You could say that, yes, the ITS project was effective when it really was not, and your results were affected by the fact that you did not account for unobserved heterogeneity in your data. And as I mentioned, there are common statistical tests that you can use to show that you determine if unobserved heterogeneity is a concern in your data. I mean, you can use like a likelihood ratio test if you're estimating with maximum likelihood methods. So unobserved heterogeneity is the first point that is going to be an important concern in this data analysis. The second one is data size and prediction causality trade-offs. So when you think of ITS data, the size of ITS data can limit the practical use of statistical models. Usually when we estimate statistical models, we're talking about a couple thousand observations, but now we have millions upon millions of observations. So that leads us to big data methods, such as machine learning. However, these methods are notorious because they do not necessarily uncover causality like these statistical and econometric methods can. So this is something that is a concern. There's a trade-off. Big data with machine learning is great prediction, but the causality is an issue. So models that predict well may not uncover causal effects very well. So when we look at the models that have been used in the analysis of transportation data, we have traditional statistical models, heterogeneity models, which I just talked about, data-driven methods, which include machine learning, and causal inference models, which are very popular in economics, but have not been used much in transportation data analysis. And the reason is that usually to control the causal effects, you have to use very aggregate data, so that limits the number of items that you can actually predict. So causal inference models have not been used much in transportation. If we look at the trade-off, this nice diagram that has the trade-off between prediction, causality, and data size trade-offs. So when we look here, let's first look at big data suitability. In this case, the data-driven methods, which are represented by the red line, have very good big data suitability. And they have excellent predictive capabilities, but they're very weak in causal inferences because it's hard to figure out what the causal effects are. When we look at traditional safety models, they have a little bit of predictive capability, not much big data suitability, and they uncover some causality. The causal inference models, which are again mostly in the economic fields, have limited predictive capability because they do not deal with the micro level data that we need to make predictions in transportation contexts. They have very limited big data suitability, but in very controlled circumstances, they are very effective on uncovering causality. Then there's the heterogeneity models, which have pretty good predictive capability, not to machine learning standards. Some big data suitability because you're using simulated maximum likelihood estimation in most cases, but not nearly as good as machine learning. But you do have a great opportunity here because they do have very good causality. They're very good at uncovering causality. So you can imagine, for those of you looking for research topics, the best analytic method for the future would be some combination of machine learning, which gives this red triangle, with this green triangle, which would be the heterogeneity models. There have been some papers recently that have tried to combine these two methods. It's not necessarily an easy task, but there's a lot of potential there as a way to handle large amounts of data, but still uncover underlying causality. So now let's move on to temporally shifting model parameters. So the issue here is that human behavior is continually evolving. And this human behavior continually evolves for many reasons. There's just natural evolution with new technologies being introduced, not just in transportation, but societal effects and so on. And you can even view the pandemic as an evolution of human behavior. So there are long-term structural shifts that are induced by continually evolving behavior. And when I wrote this, I wrote a paper on temporal instability for the safety field. This paper looked at a lot of the cognitive literature and from neuroscience and so on. There's a lot of science that goes beyond why human behavior is changing, and that the change has accelerated greatly in recent years. So in the transportation perspective, there are behavioral shifts that are induced by technological innovations. And you could look at it as there's, with all the new vehicle technologies that are coming forward, it is is resulted in a fundamental change in the way humans drive cars. Okay, so when we look at temporal instability, there's ample evidence from safety and travel behavior literature of the parameters changing significantly from one time period to the next. And there are standard statistical tests that can be applied to show why this is the case, like a likelihood ratio test if you're using maximum likelihood ratio. So if you're using maximum likelihood estimation. So ignoring the temporal shifts that are likely occurring in your data can lead to erroneous conclusions and inferences. So it's very important to think about when you're analyzing data. If you have data that's collected 2 years ago using that data to predict what's going to happen today could be problematic. And that's something that you can explore empirically, looking at the concept of temporal instability. The last point is compensating behavior. So we can look at this as that the introduction of innovative technologies, which is going to be, smart cities and ITS for sure, and also semi-autonomous vehicles. There's a lot of applications for this. It's going to change behavior in unexpected ways. And the example that I'm going to use is consider a technology that improves safety. What will happen? So you have this little diagram here. So we can say that in some initial phase, there's a trade-off. Individuals are making a trade-off between what I'll call driving intensity, which could be speed or driving distracted. I'll refer to all of those elements as driving intensity, and the probability of a driver avoiding an accident. So the way to look at this is that each individual driver has some equilibrium point where they say, okay, I'm going to drive at a speed that gives me like a 1 in 10,000 chance of getting into an accident, because that's my acceptable risk. And that acceptable risk would be represented by this point A, where you're trading off how fast do you drive, or how distracted do you drive, and what is your probability of avoiding an accident. Now, again, each individual person in your data set will have a different point A. So now, if we do a safety improvement, an ITS safety improvement, or something in the smart city that shifts this equilibrium, so this line, the line which has the marginal rate of transformation, moves to the right. And the expectation that analysts often make is that people will retain the same driving intensity, and that we're putting in this project to improve safety, so all the benefits will be for safety, and we'll move to point B. In another extreme case, you could say, well, if a person completely compensates, it's like I want to have a 1 in 10,000 chance of getting into an accident. I keep my 1 in 10,000 chance. I'll move to point C. So we'll have no effect on safety. Your safety improvement will have no effect on safety, and I'll just start driving faster or driving more distracted. Now, in reality, the points are somewhere going to be probably between B and C, something like point D. In an extreme case, though, you could have someone that grossly overestimates the safety effectiveness, and you could end up in point E, where you're driving faster and actually reduce safety. So keep this sort of compensating behavior in mind when you're trying to understand what's going to happen to an improvement that you implement. So if we ignore compensating behavior, you'll lead to an overestimation of the intended effectiveness of the safety improvement in this case, and unexpected consequences will arise that you have faster drivers, more distracted drivers. But you should have anticipated that by recognizing that compensating behavior was a possibility. So to summarize, the transportation field has entered an era of unprecedented technological innovation. When you think about what has happened in the last 4 or 5 years, even, it's been amazing. So many things are happening. The data analytics face key questions that limit their effectiveness in the evaluation and forecasting of smart city and ITS. So these are the 4 examples that I gave here. So researchers must think about unobserved heterogeneity, the implication of analysis methods. Let's get to the big data prediction, causality trade-offs, temporal shifts in behaviors, and compensating behaviors. So again, the papers that discuss each one of these topics are listed here. I have a 2016, 2020, 2018, and then the compensating behavior paper that I wrote in 2006 that looked at how people traded off when you put in anti-lock brakes and airbags. I've since applied that paper to the new technologies that we have today. So think about these 4 elements, glance at these papers if you prefer, and have a great time analyzing data because we're entering a great period.